Hello, welcome back to 2 Civil Math. I'm your host Jamie, and today's topic is using Pascal's triangle to find the coefficients of terms when expanding a binomial expression to any degree. It is arranged in a triangular array, so the numbers on top and on the outermost are ones. The remaining numbers in the middle of the array are found by summing the nearest two terms in the above row. Let me write that out so that it makes sense. So 1 and 1, 1 on top for the 0th row, and 1's on the outside for the first row. Next, we have the second row, which are 1's on the outside, summing the nearest two on top, which are 1 and 1, that gives us 2. We write outermost 1's and sum the 1's on top, so we have 1 plus 2, which is 3, 2 plus 1, which is 3. So now we have the fourth row, which is 1's on the outside, 1 plus 3, which is 4, 3 plus 3, which is 6, 3 plus 1, which is 4, and so on, so on, so on for how much you want to do. So counterintuitively, the top row is not called the first row, but rather the 0th row. This is because we need to account for any binomial to the power of 0. Anything to the power of 0 is just 1, so the only coefficient's 1. Then the row below that is the first row, and anything to the power of 1 is just itself, so the coefficients are 1 and 1. Then we add 1's to the outermost of the triangle like I did, and add the two numbers directly on top to find the missing term in the middle. You could do that for as many terms as you want all the way down. It's very easy to do so. So, I was discussing something about binomial expansion theory earlier. But what is binomial expansion theory? It is a theorem that tells us how to expand binomials in the form a plus b to the power of n. It makes it very easy to expand binomials with large degrees using the help of Pascal's triangle. Pascal's triangle tells us the coefficients that we need to use, and using binomial expansion we could write the variables correctly. It'll be easier if I demonstrate using an example. So our first example problem will be x plus y to the 5th power. Now we need to write Pascal's triangle up until the 5th row because that is the power that we have. That is the degree of the example. So the 0th row, which is 1, and the first row, which is 1's on the outside. Next, we have the second row, which is 1's on the outside, and 1 plus 1, which is 2. Next, we have the third row, which are 1's on the outside, 1 plus 2, which is 3, 2 plus 1, which is also 3. So now we need to find the fourth row, which is 1's on the outside, 1 plus 3, which is 4, 3 plus 3, which is 6, 3 plus 1, which is 4. Finally, we have the fifth row, which once again we write 1's on the outside and find the sum of the numbers on top. So we have 1 plus 4, which is 5, 4 plus 6, which is 10, 6 plus 4, which is also 10, and 4 plus 1, which is 5. So now that we have Pascal's triangle up until the 5th row, we know the coefficients that the expanded form has. Let's write all of them down so that it's easy to do the next step. So 1, 5, 10, 10, 5, and 1. Let's write addition signs all beforehand. So now, going from left to right, we have to descend the x variable starting at the degree that the unexpanded form is in. So we are at the 5th degree. So we start at x to the 5th, then descend to x to the 4th, then descend to x to the 3rd, and then descend to x to the 2nd, and then descend to x. Then we have x to the 0, which is just 1. Now, going from right to left, we have to do the same thing for the y variable, but this time, like I said, we have to descend from right to left. So we have y to the fifth, y to the fourth, y to the third, y to the second, y to the first, but that's redundant, so we can just erase that. The y to the 0, which is just 1, so we don't write anything there. That is our final answer. Let me read that out. X to the fifth plus 5 times x to the 4 times y plus 10 times x to the third times y to the second. I forgot to write another addition sign over here. Plus 10x to the second times y to the third plus 5 times x times y to the fourth, and finally plus y to the fifth. So we tackled a seemingly tedious expression and made it very easy using Pascal's triangle and binomial expansion theory. So let me move on to our second example. This is going to be very long, but it'll be very easy because we know how to use Pascal's triangle. So strap in. We have x plus y to the eighth. Scary, but this is very easy using Pascal's triangle. So let's write Pascal's triangle out once again. So we have 1, the 0th row, 1 and 1. The first row, 1, 1 plus 2, which is 2. 1 plus 1, which is 2. And then another 1. So we have 1, 1 plus 2, which is 3. 2 plus 1, which is 3, and 1 on the outside. We have 1s again. 1 plus 3, which is 4. 3 plus 3, which is 6. 3 plus 1, which is 4. We have 1s on the outside once again. 1 plus 4, which is 5. 4 plus 6, which is 10. 6 plus 4, which is 10. 4 plus 1, which is 5. Now we have to write 1s on the outside again. So we have 1 plus 5, which is 6. 5 plus 10, which is 15. 10 plus 10, which is 20. 10 plus 5, which is 15. 5 plus 1, which is 6. Now we have the 7th row. We have 1s on the outside once again. 1 plus 6, which is 7. 6 plus 15, which is 21. 15 plus 20, which is 35. 20 plus 15, which is 35. 15 plus 6, which is 21. And 6 plus 1, which is 7. Finally, we have the 8th row, which is 1s on the outside. 1 plus 7, which is 8. 7 plus 21, which is 28. 21 plus 35, which is 56. 35 plus 35, which is 70. 35 plus 21, which is 56. 21 plus 7, which is 28. And 7 plus 1, which is 8. That was a process, I must say. But now we know all the coefficients for x plus y to the 8th. I'm going to erase everything besides the 8th row. Before I do so, I will tell you a little trick that makes it easier to denote which row each thing is on. So the second term will always be equal to what the degree of the expression is. So if we're finding the 8th row, we don't need to count down 9 times, but rather we can look at the second term and see, oh, that's 8. So we know that has to be to the 8th degree. Or if we had x plus y to the 4th, we could be like, oh, this is 4, so the second term is 4, that's the 4th row, and now we know all the coefficients. So you could do that for anything, including the 0th row, because if it's to the power of 0, the second term is just 0, so we know is going to be x plus y to the 0. Can we erase everything above there? I kind of hit the 8th row, but it's okay because I got to rewrite them anyways. So if 1, 8, 28, 28, 56, 70, 56, 28, 8, and 1. Alright, using binomial expansion theory, we go left to right, descending the x value. So we start at x to the 8th, x to the 7th, x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x squared, x, and x to the 0, which is nothing. 1. But we don't multiply that on. Now we go right to left descending the y. So we start at y to the 8th, then y to the 7th, then y to the 6th, then y to the 5th, then y to the 4th, then y to the 3rd, then y squared, then y to the 0, which is just 1. Finally, we add addition signs in between everything. So we have all of this here. And we just solved that very tedious binomial expression using Pascal's triangle, and it made it very easy. So our final answer is x to the 8th plus 8x 7th to the y plus 28x to the 6th y squared plus 56 times x 5th times y 3rd plus 70x to the 4th y to the 4th, 56x cubed times y to the 5th plus 28x squared y to the 6th plus 8xy to the 7th plus y to the 8th. And once again, I forgot an addition sign. But that is our final answer. Okay, now we are going to tackle something a little bit tamer in terms of degree. But this is when one of the terms is not equal to 1 in the binomial expression. So what do I mean? We have x plus 3y to the 6th. This is going to be more tedious than first example, but first, if we find the formula for x plus y to the 6th, it'll be very easy to just substitute the 3y into the expression. So we still need to follow the same process of finding the coefficients on the Pascal triangle, but now we have an extra step. So we got to find the formula. Let's rewrite Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and finally 1, 6, 15, 20, 15, 6, and 1. I know this is the 6th row because the second term is 6. So I'm going to erase everything above the 6th row for sake of space. So let's rewrite all the coefficients. 1, 6, 15, 20, 15, 6, and 1. Now we could erase this as well because we know all of the coefficients. So now let's descend the x term going left to right. So we have x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x squared, x, and x to the 0, which is just 1. Now going from right to left, we could descend the y term. So y to the 6th, y to the 5th, y to the 4th, y to the third, y to the second, y, and y to the 0, which is just 1, so we don't need to do anything about that. Add addition signs in between everything. I'm not going to forget this one this time. Har, har, har. Now we have all this. So now we know the parent, not parent function, but the formula for what it would be for x plus y to the 6th. And now, very simply, all we got to do is substitute the 3y into everywhere that is y in the formula. We don't do that for x because the x just stayed the same. So let's divide this so we could have a visual separation between the formula and the actual answer. So we have, I don't need to write the 1. So we have x to the 6th plus 6 x to the 5th times 3y plus 15 x to the 4th plus 9y squared. All I'm doing is substituting this y for this y in the binomial expression. And I'm just going to skip an extra step by already doing the calculation for 3y squared. So it'll save us time later. 20x squared times 27 y to the third. Oh, you could barely see that, it's fine. Plus 15 x to the 4th oh, excuse me. 15 x to the 2nd times 81 y to the 4th plus 6x times 243 y to the 5th, because 3 to the 5th power is 243. And then finally we have y to the 6th, which is just 729 y to the 6th. And now if we substitute, simplify everything here, we don't need this anymore. So I'm just going to write the answer up here. So we have x to the 6th plus 18x 5th y plus 135 x to the 4th y squared plus 540 x to the 3rd y to the 3rd plus 1215 x squared y to the 4th plus 1458 x y to the 5th, and finally 729 y to the 6th. That is our final answer, and holy, that is not neat. I apologize for that, but this is our final answer. So, in summary, you could expand tedious binomials using binomial expansion theory and Pascal's triangle to find the coefficients. Thank you for watching.